I'm very excited to be here today. Dimitri didn't know how to introduce me because I had no bio, so I'll just give you a background. I grew up here in the Valley. I've been here so long that I remember the day that Texas Instruments laid off a bunch of people that were in their factory making electronic watches. That's how far back I was a kid. So I've been through a bunch of different industries and done a lot of startups in the Valley. And I'm come to TidalScale because I think it's a very exciting, game-changing kind of a technology. First thing to say about TidalScale is the team is a fantastic team. I've now worked with 16 of the smartest people ever. They're just fantastic. All very low level, mostly in kernel development. Some guys you may remember or know, Dr. David Reed, he's our chief scientist. He's the guy who has a law named after him, Reed's Law, which is the theory of networks, economics and networks. Dr. Ike Nasty, he's formerly was the chief scientist at SAP, and tremendous amount of experience on the team. We're backed by some very good venture capital firms, really good team around us, and so really sage advice that we're getting from that team. So what is TidalScale? So TidalScale is about removing constraints. So most of the talks we have heard at this conference have focused on the fact that you have some tools, whatever, pick your tool of choice, you get up to a certain size, it all assumes everything's in memory. And then you have to switch to a different solution. You have to start scaling out. So you have to switch to a different set of tools to actually do that scale out across the memory of many machines. What TidalScale does is it removes that impediment. It actually lets you take the first set of tools, the ones that are assumed in memory, and just keep getting bigger and bigger machines. So at the high level, it's a very simple story, which is we just give you big in-memory hardware, in effect. We do it through virtualization, but it's a scale-up story. So what I'm going to talk about is generic to any problem that requires a lot of memory. So the ones that are most hardware that I've seen are data mining, like graph analysis, simulations, bioinformatics. Those kinds of areas really benefit from having a large memory. We'll get to the end. I'm going to go through some detailed benchmarking we've done on R, which is a statistical package that I'm sure everybody's familiar with here, but it's also pathologically in need of memory. And so for my purposes, it's an interesting application for us to test. So how do we do this, you say? Because this is really quite not the usual thing you're going to hear. Today, as all the scale-out kind of frameworks will tell you, the solution to getting bigger data today is in your application. You design your application so that chunks of the big data problem are actually on different physical machines. And so you're managing that explicitly. With TidalScale, what we do is we have a product, it's a hypervisor, it's a virtualization layer that sits underneath the operating system. And we manage the distribution of work across the physical machines. And then you boot your unmodified guest. And by unmodified, literally, we're booting the CentOS ISO that you get off the web. It does not know. It just sees the add up of all the hardware resources underneath. And so what you get at the end of the day is the same user experience as what you have today. The only difference here would be that you would see when you log in under TidalScale, it's a much bigger machine. That's literally the user experience. There's no API, there's no hint, there's nothing you have to do other than boot your guest and do your job. And it'll just appear that you have a lot of resources underneath that. So just to cement that further, we are not a scale-out software solution that you have to program to. It's not a job scheduler for data centers. It's not about storage. It's just about single large computers. It's not magic, and I'll try to explain why it's not magic to make it more clear, and it's working today. Okay, so why does it work now? Because this is, the problem we're addressing is a problem that has been a limitation in computer science for 40 years. Number one, what TidalScale does is systematically apply Dave's locality theory at a cluster level. So locality is about the fact that processors tend to get the data they most recently accessed tends to be the data they want next. And so when you're trying to optimize the performance of the CPU, you want all the data it needs to be there, reduce number of cache misses, all that. We apply that across a cluster, but we have mobilized all the compute resource types. So for us, a processor isn't the hardware processor. We have a virtual processor. And that vCPU can float across a cluster. So if you're trying to build a locality set around CPU 1 and he needs a page over on node 3, we can actually pick up that processor, take it across a 10 gig bus, drop it on the other node with very low latency, and then it has local access. So it's systematic application of locality set. The next reason it works now is in the last 3 or 4 years with BTX and BTD, you have a lot of hardware acceleration circuitry put into getting memory in and out of a processor. This is in support of virtualization, and we're a kind of virtualization. So this makes it possible for us to actually transfer resources quickly, like a page of memory, pick it up, drop it, get it into another processor. And then the third thing that's changed in the last 10 years is if you look at the memory hierarchy, and maybe I should back up. Let's go here. There's a great book called Computer Architecture that goes through the memory hierarchy and takes the actual latency in nanoseconds. So you see a CPU cycle is 0.3 nanoseconds. Level 1, 2, 3 cache access are all multiple nanoseconds. Main memory access is 120 nanoseconds. But then it does a really cool thing is it scales that as if one CPU cycle were 1 second, and then gives you in human terms what the latency means. So if you follow along the scale column on the right there, you'll see one CPU cycle 1 second. Level 1, 2, and 3 cache access is sub a minute. Scaling it up to follow the nanoseconds. Main memory access is 6 minutes. Solid state I/O is 2 to 6 days, and that's the best case. That's if you hit the cache in the flash device. And then storage is months, and then I love the one that's a TCP packet retransmitted, 100 to 300 years. So this gives you a sense of the effective latency on a processor's efficiency. So if you chart that over the last 10 years, this is the same data in nanoseconds. This is CPU register, this is SRAM, this is main RAM. Notice how it hasn't really changed a lot. And then up at the top, there's a lot of storage devices, but the line that's changed the most in the last 10 years is actually network. And that's the blue line. And network is kind of on par with storage if you're using normal stack. The way we use it is that last data point. And you can see we're much faster because we're right on the wire. So the way we use it makes it actually very, very fast for getting something across the network. So TidalScale effectively creates a level 4 cache in software. That is, if you are getting a VM exit and have to go get a page of memory from another node, that'll take you some hours, but it's not days to months like SSDs. And if you have to transfer CPU from another node to a locality set you're building on another node, it's it's on the order of hours, not days to months. So we've implemented a level 4 caching software that lets you run these loads. And the premise is that if I've got a 100-step operation, if I pause for a step to transfer everything to be local on a node, those 100 steps can now all run on local resource latencies, leveraging the rest of the cache hierarchy. Any questions on that? Because this is the core concept. Yes?
So you need in-house cluster.
Well, this is assuming you're putting a bunch of servers together, yeah, to make them a single machine. Yeah. This is a rack level solution. So you take, 35 servers in a rack, and you make them boot as a single machine. And whatever size your server's there, that's how big the machine will be. This is what we need. So it doesn't work across data centers, if that's what you're asking. Yeah. Other questions on that? Make sense? Okay, so let's go through what that means. So an example, if you get a standard server, 2-socket server with 24 DIMM slots, this is going to be our Lego building block. And we're going to take 8 of those and make a 3.2 terabyte system. So you rack them up, and you hook them up with a network. We use the 10 gig resource. 10 gig network is a resource interconnect. And when you tell the management console of our system to boot, it'll Piercey boot these servers with our HyperKernel. And then the HyperKernel is stitched together to make a single big machine. And then you boot your normal guest OS and the rest of your application stack. And what the guest OS is going to see is actually an add-up of the resources of those 8 servers, or however many servers you put together. So we just give you big machine. And the interesting thing about doing it this way is that for larger data problems, we kind of lower the cost of doing large systems. So the blue dotted line here is actually standard server hardware purchased online or without any major discounts. These are all list prices. But you can see across the bottom here is the system size in terabytes. So as you go up in system size, you can see the cost goes up. And the bend in the curve here is when you have to go to higher density RAM DIMMs, effectively. So as you go to larger and larger single systems, you can see the cost gets much, much more expensive. With TidalScale, you basically stay on that lower cost curve because you're able to take multiple D servers and then add them up to larger and larger systems. Not only that, but as you add up to larger and larger systems, and the largest one you can get from Intel is 6 terabytes there. Those same comparisons of systems here, you can see the 6 terabyte system only has 60 cores. Whereas with the TidalScale system, because you keep adding servers, you're actually getting more and more cores. So there's a potential benefit here for many processors as well at the same price point. And the other thing I should point out is the comparison of prices. So about $500,000 for that 6 terabyte Intel system. And ours, including hardware and software, would come in for about 40% of the cost of that. So talk about use cases. Generally, the kind of use cases that benefit from large coherent systems, data mining, bioinformatics, simulation, and the one that seemed to have a lot of need for large memory, in particular, in machine learning was R. So R is a fantastic application and platform. Its key assumption, though, is that all objects that it's working on are stored in memory, unless you explicitly program. And the problem with the distributed computing in memory computing is it's very hard to do well. And there's a whole class of problems that actually just you don't get the same quality of answer or result. So R is a great test case for our system. So we went and found an open source data set from the Center for Medicare Services. It's a set of healthcare and insurance claims. It's about the total number of files total is about 70 gigabytes in raw data. And then after you do the set of operations we chose, you end up with almost 700 gig in memory. So this gives you a very scalable test case, and we use it internally to scale across different sizes of nodes. The problems we applied this to was generalized additive model, generalized linear model, k nearest neighbors, random forest, and decision tree algorithms. And what we have done is compare the results on a 128 gig physical server with a 5-node TidalScale tidal pod. And the goal is to demonstrate the scalability of our system. A little more in the data set. It has a number of tables and records. It's a pretty big data set. And when we run those 5 algorithms, and you watch the resulting in-memory size, as we scale the number of samples in, you can see the resulting size in memory. So it goes from 34 gig to almost 700 gig when you're looking at top in the OS. So here's a result on the 128 gig server. It goes up to about 108 gigs, and then it has to start paging, in this case, from fast SSD. And so you can see it's much slower performance times at the larger size.
The y-axis.
Oh, sorry, the y-axis is a log of time, and the x-axis is a log of in-memory size. Right, so as you increase the memory size, it's taking longer time. And the reason I did log is actually the patterns are much more visible that way, because otherwise it gets really noisy at the low end, and then it's not interesting. So in our case, knowing that it takes 158 days to do that first large data point, we turned off swap. We actually wanted to turn off swap so you don't have any influence on the result. So this is just the physical 128 gig server, and we've turned off swap, and so the job fails. R says, I can't get the next 3.2 gig of memory. I'm sorry, I'm dead. Or sometimes Linux actually kills the job. I don't know which causes which, but anyway, I've seen both kinds of errors. So you run out of memory, the job fails. And that's kind of the physical server. So beyond this size, you would need to go rewrite your R application to go across physical servers. This is the TidalScale line. So you can see we have some overhead here. It's about 1.7 of the hardware speed, but it's going out past the physical limit of the server. And the part of the line to the right, this is not a marketing chart, so it probably understates the value here, but what's happening is you're going across 2 nodes, then 3 nodes, then 4 nodes, and the last data point's on 5 nodes. So it's being smeared across 5 physical servers. Those vCPUs are floating around, the memory's floating around, and it's actually delivering that kind of linearity in performance. If I was going to compare that to paging from storage, I have to add a couple orders of magnitude back to the chart. And the lower purple line on the right, that's if you were running this with a fast SSD. So it's about 300 times faster than a fast SSD. And then the line on top is with normal disk drive storage. And then putting them back together. So here, I put the TidalScale performance curve right up against the paging equivalent. So literally the memory clip that people talk about. Questions on the benchmark? Yes?
It's a 5 server.
This is 5, yeah, it's a 5 server Tidal, yes.
So how does it apply to maybe even larger server cluster? Can you keep this linear so good scaling when you have like 32, 64?
Well, that's the theory, yes. I haven't tested 32, no.
What's the biggest you ever tested?
Biggest we've tested was 12, and I haven't had a chance to test this on 12. We were doing a different test. The testing challenges, there's a lot of things to test, so we're running a bunch of stability bench tests like L2P, Linux test project, mem tests, a bunch of stress tests, and then we're also doing these benchmarks. I'm working on right now writing a Python benchmark, Python data mining benchmark. So if you guys have opinions about what would be a good scalable data set to test, that would be very handy to me. The challenge with this benchmark was finding a data set that actually scaled out to something big enough to be interesting. Because your standard server, you can get a 384 gig or 768 gig server that's pretty affordable. And then you add up 5 of those, and it gets pretty big. So our biggest system is 7 terabytes. That's a 5-node times 768. And data sets that are big enough to actually stress that at full scale are actually open source data sets that don't expose any personal data that are that big are kind of hard to find. So the one I'm looking at for Python is trying to do a cluster analysis on Reddit comments. There's a data source online available, but it has 5 years of history of Reddit comments, and that gets pretty big. So I don't know how big that is. I'm actually actively working on that now. But in theory, this can keep going because each vCPU can collect its own locality set around it and go someplace where it's got room to be and work. But the way that the vCPUs can float around the system means that you can have vCPUs actually share locality sets and at times have them be separate. So the whole name TidalScale came from the idea that the systems could flow around, the resources could flow around the system as needed, kind of like the tides. That's where the source of the name came from. Other questions about the benchmark? I had a question for the audience, actually. So I picked these 5 algorithms to test. Are there suggestions for other things that we should test or add to our test rig for R? So again, GLM, k-nearest neighbors, random forest, decision tree. Do you guys have other algorithms that are in need of large
marketing? You're talking usually maybe collaboration filtering, association rule mining. Okay. All the algorithms are underground, so it's easy to implement. But those are some things we use.
Collaboration filtering, and what was the second one?
Association rule mining.
Okay. Next question. So, is this useful to you as data scientists, removing the constraint of a single machine? And what other use cases would you suggest are areas that this would benefit? Yes?
First of all, for models, I would suggest maybe different clustering models, basically running on the wall networks. There's so much they can be pretty messy. And if this is useful or not, I can say yes, it seems pretty useful because for one of the projects that I'm working on, we are actually trying to make sense of video files, which are more than 17 years of video streaming. And for doing that, we are actually facing lots of difficulties, especially for memory analysis.
Deep memory. Okay.
Something like this can definitely be helpful. But my question is actually, the data still needs to be pulled out of the database and being so because I was talking to this gentleman from Microsoft, and it seems that in SQL 2016 they are actually offering this in database analysis, which basically lets R being implemented and being run on each other distributed servers instead of just collecting all data and organizing at the same time. So by having such a technology, do we still need something like this to connect with all our machines as well? Because we can definitely, basically based on their theory, we can actually do all this analysis of each of these codes and just probably solve.
Right. It depends on the problem, right? This is just another tool in your bag. And the tool in this case, so the question was, can't we just rely on in this case, SQL server enhancement that's going to automatically scale out? And the answer is that will work for some problems. It depends on your problem. There's a class of problems where it's very hard to slice it up and put it across the machine because the communication between the nodes, if it's a problem where there's a lot of dependencies, it becomes very high and it gets slow. So the other way to think about it is what we're doing at the very, very low level here, shifting resources around a page at a time without anything in the TCP/IP stack, right? Because what's going over that 10 gig interconnect is just raw Ethernet frames. So it's very, very fast down at the low level. And if you have a problem where there's a lot of intercommunication required between the chunks that you define at the higher level, you're effectively competing with all of the TCP/IP stack, all of the application stack, all of those overheads, and having to send chunks against all, across the servers against our frame by frame, highly performant, low latency. You can see there's just a lot of overhead trying to do that at the application layer. So this tool in your bag is for the problems where there's a lot of intercommunication requirement. So take a simulation. In EDA, when you design a chip, you have to do a thermal simulation. And you want to see that this tracing through the chip generates this kind of heat around it, and that's going to affect this other circuit below it. Well, you can take the thermal simulation of a circuit, put it on one machine, thermal simulation of another circuit, put it on the other machine, but then how do they interact? It gets very, very high communication requirement between elements. So there's kinds of problems where that fits. So bioinformatics, simulations of any kind, and data mining where the bigger the graph you can hold in a single machine, the more patterns you can see. That's the kind of problems for it. But it's just a computer. So anything that would benefit, I'm not, you could still run SQL on it. Yeah, big fat nodes, I guess. Right. Other questions?
Actually, I have a comment about the question. So at my client, we use RRA, which is the Microsoft SQL database. I guess probably for our jobs, and we use Spark R. The problem with RRA, which you don't know when you sort of sign up for the service, is that they are rewriting a lot of the algorithms that you are trying to actually use. So a lot of the algorithms that you do data mining with, like association rule mining or collaboration, are actually not available in RRE. So maybe about 11, 15 algorithms that you can actually parallelize in Microsoft RRE are available. But a lot of other things are not. The way I see this, you sort of circumvented all of this rewriting of the code to be parallelizable, and you are actually offering everything available in CRAN and in R to be parallelizable and multi-threaded. That is something we RE actually lacks, and even if you go to Spark R, you have the same problem because you're limited with the number of available algorithms that you can actually multi-thread. So
that's correct.
So that is a very big difference between your technology and what Microsoft and others are offering.
It basically saves you a lot of application coding work getting a scale-out version of the application running. You can get it working on your laptop and then literally run the same job on a 10 terabyte problem without changing the code. There's a UCSC research paper that was published, a similar idea, where the guy took a Hadoop job and ran it across 10 nodes. And then there's an open source tool that will let you take a scale-out job and recompile it as a single job, and then ran it on a big machine. And it was 10 times faster. The same job, actually, was 10 times faster on a single machine. So that supports your argument. Yeah, other comments, other use cases, other benchmark ideas?
Have you tried complex simulation problems?
Yes. Any logic? It's a simulation they ran was a disease propagation simulation, and generally the benefit I would say from a data scientist point of view is the larger the single machine you can do or you can get to, the more fine-grained your model can be. So in this case, it was this disease propagation analysis, but they could only get to the kind of a third of the town size in terms of number of agents. And with the big system that we have hosted, they were actually able to get to a whole town. But their vision is do disease propagation like Ebola, that kind of stuff, for the whole U.S. And ultimately the world. So it's to get it down to the level of an individual just requires a lot of agents, and that benefits from having a very large machine. In fact, that gets me to what I would like to kind of pitch to you guys is we have 3 proof of concept systems. We're in beta. We're trying to ship our 1.0 in the next month. And we are really, really aggressively interested in trying different large workloads. So we have 3 proof of concept systems available. And they're down at the Exchange in Santa Clara. They're hosted. Literally what we would do is we get your SSH key, give you a authenticated login, and you become root user. You would own the whole system. It's just a stock CentOS 6.6. And you can install whatever you want to install and just try it. And if you got a big data set, you can send us a disk and we'll preload it for you. We also have a way to upload it if it's smaller, just over the network. And if you've got a big data load that you just want to see, would it work on this? We're as interested to find out as you would be. So we invite you to come try it. The guy to talk to about getting scheduled, because we got a lot of interest on this, is Tom Miller. That's Tom. And you should come talk to him about that. But I'm really interested in getting a variety of workloads to test. Like I said, we're doing a lot of testing and always trying to tune for best performance. Like even the chart I showed you, we're dissatisfied with that. We would like this overhead to be on the order of 10% and then have it scale up. So we're actively working on the performance story and knowing how your application would work on our systems is very interesting to us. Any other questions? Yes?
You tried just reading the Excel files or any HDFS file system as well or any database? Like read the data.
So the question is, have we tried to read any?
So when you did the performance benchmark,
Yeah.
were you only reading data from Excel files or any databases? Or
No, this one, it's actually CSV files. The download you get from the CMS government site is a bunch of CSV files. So the operations literally, we're timing, when we time it, we actually are timing the read, the join time, and then these 5 steps. So we didn't cherry pick. It's the whole, typical workflow you would face as a user. And so this is, the result time that I'm showing here, it is actually including the whole workflow. The point I was going to make about that I thought was interesting to point out is you get all of the resources. So from an I/O point of view, the fact that there are 4 1 gig Ethernet ports on every server in that title pod, right? You get all of those ports on those servers. So when you boot the guest, you'll see 32 Ethernet ports that you can then bond into a very big pipe. So there's actually performance benefit from an I/O point of view, which, depending on your use case, could be also quite interesting. Other questions? Yes.
So the final product would be the hardware that we provide?
No, it's software only. It's just the little pyramid things. It's just the hypervisor. So we sell, literally, it's a USB key, and you come and plug it in. You physically set up your stock servers. You come into the management console server, and you put in this USB key, and then you install it from that. And then we unfold everything we need to make it work.
So it's not like a solid different TS admin management console. It's not some hardware.
Well, it's a different system, but it's not an appliance. We're just, it's a 2 gig USB key, and then it unfolds, and you have to have the things hooked up right. And that, and the little things like the 10 gig network has to be jumbo frames turned on. There's some configuration to do, but otherwise it's just a piece of software deployed on a cluster, but it assembled a different way.
Would you be offering this as a cloud service maybe in the future? Or?
We're investigating that, and it depends on the results. We're investigating that. But right now we're just selling the hypervisor. We're mostly focused on premises because this has to be on the metal. So it won't work on something in like Amazon Web Cloud Services. It wouldn't work there because they have virtualization underneath, and we need to be on the hardware. Yeah.
I just want to make a point. We are actually very actively looking at options to be able to deliver the sort of TidalScale as a service. So while we haven't got anything announced, it would be helpful if you're interested in this and had some guidance or had a particular use case that was use case and potentially a partner that you'd recommend to work with to help deliver a TidalScale as a service. That's something we'd be interested in hearing about as well.
Yeah. Other questions? Yeah.
Any plan to abstract GPU too?
It's possible, but it involves yet another set of testing platforms for us. So we're a small company, we're just trying to get 1.0 product out the door. But you could imagine a world where you had CUDA cards in all of these, and they were pounding on a single memory image. Yeah, that's possible. But then, I've got to pick a card and certify that and test that. And, it's just down the road, sure. Other questions? Okay, well, I will leave you with the invitation. Please come talk to Tom if you're interested in testing. We really would like to try it out. Thank you very much. Oh, yes, one last thing.
Do you have the GitHub address?
Oh, yes,
for
I can
the
show you something else that's
benchmark?
cool. So that benchmark, I know you're data scientists, and one thing I've learned about all my interviews with data scientists is they like data. So what we did was we took the whole benchmark that we had developed, and we put it up on GitHub, and along with the analysis results. So you can actually go search this, find this, you can see exactly the code. You can tell us if we got it wrong. The one caveat, if you go to try to run this, is I have to add another bit of documentation about how to use a testing framework that we use internally called nose test. So if you actually go try to run this, it'll complain it doesn't have nose test, and I need to add that document. But otherwise, it's all the code we're actually running internally and the results in a white paper with the details.